Hi, ladies and gentlemen. Let me welcome you to the 11th session on ECT 204 Signals and Systems. Today we see more on convolution integral. This is a short speech with the contents being your learning outcomes, the linear convolution integral, and the convolution of two pulse signals, then the summary of understanding. Now in this video you will learn the continuous time linear convolution with examples. We are basically computing that convolution integral for a few cases. Now let us consider the linear convolution between two exponential signals. Consider a continuous time system with the impulse response say ht equal to say e raised to minus alpha t ut. This exponentially decaying signal, ut is your unit step, driven by the input xt equal to e raised to alpha t u minus t. Okay, this is a flipped signal exponential. This for alpha greater than 0. Now the output of the system yt will be xt convolution ht, that will be minus integral minus infinity to infinity x tau ht minus tau d tau. Now if you look at this signal, this is your x tau. What is your xt signal? Xt is e raised to alpha t u minus t. So x tau will be e raised to minus e raised to alpha tau u minus tau. So this is the tau axis, this is the minus tau axis, this is e raised to alpha tau. And what is ht? E raised to minus alpha t ut. So ht minus tau will be this. This is ht minus tau. This is e raised to alpha t ut. This is for t less than 0. This is ht for t less than 0, e raised to minus alpha t. Because ht is flipped by, ht was originally this, h minus t will be flipped version here. So this is for t less than 0, this is for t greater than 0. Now we have to compute yt. And for t less than 0, this yt will be xt convolution ht, that is minus infinity to infinity integral e raised to alpha to ht minus tau d tau. So this is minus infinity to t, because this integral is from up to minus infinity to t. For t less than 0, this integral is from minus infinity to t. So this is from minus infinity to t, e raised to alpha tau, e raised to minus alpha into t minus tau d tau. So out of this e raised to minus alpha t comes out of this integral, because it is not a function of tau. So then minus infinity to t integral e raised to 2 alpha to tau d tau. So when I integrate this, it becomes e raised to 2 alpha t divided by 2 alpha. So 1 e raised to minus alpha t will be cancelled. So this becomes e raised to alpha t by 2 alpha. So for t less than 0, this is for t less than 0, it is 1 by 2 alpha e raised to alpha t. The curve looks like this. This 1 by 2 alpha e raised to 2 alpha e raised to alpha t. And for t greater than 0, yt will be xt convolution ht, that will be minus infinity to 0 integral h to x to h t minus tau d tau. That will be like this. That is from 0 to t. So for t greater than 0, ht minus tau looks like this. It is value is from minus infinity to t. This is actually from minus infinity to 0, because x tau is from minus infinity to 0. This is from minus infinity to t. So when a non-zero product occurs from minus infinity to 0. So that is from minus infinity to 0, x tau h t minus tau d tau. So it becomes minus infinity to 0, e raised to alpha tau, e raised to minus alpha into t minus tau d tau. So out of this e raised to minus alpha t comes out, and this integral is from minus infinity to 0, e raised to 2 alpha tau. This becomes e raised to, for the upper limit, it will be e raised to 2 alpha tau by 2 alpha. So upper limit only applies, because lower limit leads to 0. So upper limit is e raised to 0, that's a 1 by 2 alpha. So this integral ultimately defaults to 1 by 2 alpha. So 1 by 2 alpha e raised to minus alpha t. So this is a shape. This height is 1 by 2 alpha, and this decreases like this. So this is the shape of the output yt. Now consider another case. There is a convolution of two pulse signals. Let us consider the convolution between xt equal to ut minus 3. This is a pulse of width 3. So this is from 0 to 3, it is 1. And I have ht that is equal to ut minus 2. So this has a width of, this starts from 0 and a width of 2. So h minus tau will look like this. This has a width of 2, but flip the other way in the negative direction. H tau has a width of 2. This starts from 0 and ends at 2. So from here to here, this is the negative time reversed version of that. That is h minus tau. That is from minus tau to 0. Okay, and when I move this h minus tau from minus infinity to infinity, we get this convolution integral. We can see that from minus infinity to 0, this convolution integral will be 0, because there is no overlapping between ht minus tau. So this is ht minus tau. This is delayed by t units, or this is shifted by t units. So for t from minus infinity to 0, this will be 0, because there is no overlapping region between ht minus tau and x tau. There is no overlap between minus infinity to 0. So from minus infinity to 0, the output yt is as 0. Now we have to see this convolution as this moves from t equal to 0 to infinity. Now for minus infinity less than t less than 0, x tau ht minus tau is always 0, because making yt equal to 0. For 0 less than t less than 2, that is for the width of this pulse, as this pulse enters into this, this convolution should increase, because it is 1 times 1 integral 0 to t 1 times 1 dt. That is integral from 0 to t 1 times 1 dt. So that is t. So this happens from 0 to 2. That is from 0 to 2. This is the curve y equal to t. So that is a straight line with a slope 45 degree. So this will be reaching 2. So what happens at t equal to 2? This has completely entered into this curve. When at t equal to 2, that means this smaller rectangle has completely entered into this rectangle. So from 2 to 3, what happens is this stays at 1, because there is no more increase, because the width of the second pulse is 2. It has entered into a pulse of width 3. So from 2 to 3, what happens is it stays at 2. From 2 to 3, it stays at 2. And what happens beyond 2? Beyond 2, what happens is, as this moves, what happens is this pulse goes out of this pulse. So the overlapping region gets reduced. So naturally the convolution has to come down. So what happens is from 3 to 5, from 3 to 5, what happens is, because this has a width of 3 and this has a width of 2. So only at 3 plus 2 equal to 5, the output becomes 0. So from 3 to 5, what happens is 3 to 5, it is from t to 5, integral is from t to 5 1 dt. So it becomes a 5 minus t. Okay, 5 minus t. That is the shape of this curve. At t equal to 3, 5 minus 3 is 2, and at t equal to 5, this becomes a 0. So this reduces like this and becomes 0 here. Beyond t equal to 3, there is no output. So yt has a shape like this. Okay, if both these rectangles have equal width, say suppose both of these have a width of 3, then the output will be a triangular signal with width 6. So here you can see that this pulse has a width of 3, this has a width of 2, so this resulting convolution has a width of 5. Okay, so if this has a width of 3 and this has a width of 3, then the output will be a triangular pulse with the 6. So this is how this happens. Now let us see some simple examples with the programming. You can appreciate this code. I will run this code. Now this is a I will open a terminal here. I will zoom it a little. Now this is a case we discussed in the beginning. Here you can appreciate this code. I have specified two time axes from 0 to 500, and this is from minus 500 to 0, and alpha is a 0.009. So I have a concatenated axis for ax, and I have this x equal to e raised to alpha t2 and h equal to e raised to minus alpha t1. Now I observe the convolution between x and h. Now this convolution comes from the psi pi. I have a function convolve comma y. So these are plotted. So in as three subplots, you can see here. You can see these functions. Okay, this is the input. This is your impulse response, and you can see that this is of the form 1 by 2 alpha e raised to minus alpha t, e raised to alpha t, for both positive and negative axes. So this is what we have seen in the numerical. Now let us consider another case. Now this program shows a convolution between two pulses. See, this once 5 means it is it simulates a pulse of width of 5, and this simulates a pulse of width 3. Okay. Now we said equal to convolve x comma h. Convolve is a function from psi pi, and we can in these three subplots we plot x, h, and z. So we will run this code and appreciate this. This is conv 2. Now this is the second problem we have seen. This is a pulse of width say 4 unit, and this is a pulse of width 2 units. So the resulting waveform, the resulting convolution output looks like this. It has a width of 6, that is this 4, and this is 2, that is 4 plus 2, 6. Okay. So this is how this happens. Well, if the width of the pulses are equal, then the convolution results in a triangular signal. Here you have x is a width of 5, h has a width of 5, and the convolution will be a triangular signal. We will see that. I will say run conv 3. Now you can appreciate this. Here this is a first pulse. This is a rectangular pulse of width 4, and this has a width 4. Actually range 0, 4 5 means there are values from 0 to 4. So this has a width of 4, this has a width of 4. So this has a this is a triangular signal of width 8. Okay, this is how I demonstrate the continuous time convolution with Python. Now coming back to my presentation. Now the summary of understanding: in this video you understood the continuous convolution with the two examples, and you appreciated the demonstration with Python, and that is the end of this presentation. I thank you all.